Okay, so we're going to start with some examples from the book, section 8.2 on sequences. So let's go ahead and look at a few more examples. One of them, I did number 1 and number 4 in class today. Let's look at number 15. This is on page 692. Holy cow, we've learned some calculus, haven't we? But anyway, they've got the sequence 1 plus 1 over 3n to the nth power. So that's a 1 up there. This sequence, we want to look at the limit as n goes to infinity. Now, it does give a hint. This somewhat looks like the e limit as n goes to infinity. They have in the book, they have the limit as x goes to 0 of 1 plus x to the 1 over x equals e. But we had on the sideboard in class, we have limit as n goes to infinity. If we take the reciprocal of each of those, of 1 plus 1 over n to the nth power, this also exists and equals e. So what we want to do is we want to kind of write this like that. But if you notice, instead of an n, we have a 3n. Okay, so I would really need the limit as 3n goes to infinity of 3n to the 3n power. So what I really need here is I need to put a 3 in there to make it match. And then, of course, if I do that, I would need to undo that by taking it to the 1/3 power. Okay, so basically, what does this do as the limit as n goes to infinity? The inside part is just going to be e, right? So this ends up converging to e to the 1/3 power. So anyway, that was kind of looking at if it's convergent. It is convergent, and the limit would be e to the 1/3 power, or the cube root of e, depending on how you want to write that. So we do have that kind of manipulation trick there. So let's look at a couple other ones here. I do want to look at number 23 in the back, or 23 in the book, because the back of the book would be wrong on the way it's written for part B. But let's look at A. Part A is 3n squared over 6n squared plus 1. And we have this sequence, and we're trying to find the, it says estimate using your graphics calculator. We don't really want to do that. You know, any of these we can figure out what the first few terms are. So if I was doing that, it would be, you know, if n equals 1, we plug in 1, we're going to get 3 over 6 plus 1 is 3 over 7. If we plug in n equals 2, 2 squared is 4, so that'd be 12 on top, and then 25 on the bottom, etc. So we could plug in n equals 1, n equals 2, etc. So get a feel for the real values of the sequence there that are going. But we don't have to do this. Ultimately, if we're just trying to figure out what it approaches, we can use some of those math tricks. So if you remember, I said, hey, we can divide top and bottom by the biggest power of n when we have a fraction here. So ultimately, I'm going to get 3n squared over n squared on top, and then 6n squared over n squared plus 1 over n squared. And that's because I'm dividing the bottom by n squared, but laws of fractions, I can split up that denominator, right? So then, of course, what we have here is those cancel out to 1s, these cancel out to 1s. And so we're going to take the limit as n goes to infinity of this thing here. Well, what happens is we end up, this goes to 0, and this goes to 3, that goes to 6. So it doesn't matter how big n is, n squared over n squared is 1, right? So this ends up being equivalent to 3/6 or 1/2. So it is a convergent sequence, and the limit would be 1/2. Okay, so that would be if we were graphing this thing. If this was a function of x, of course, as a function of n, it's dots. But ultimately, what's going to happen out as x approaches infinity, we're approaching a height of 1/2, and then we can just determine if you're a little bit above or a little bit below that value. Well, since we would have something a little bit bigger than 6 on the bottom, because I'm adding 1/n² on that, I'd be just a little bit bigger than 6, so I'd be just a little bit less than 1/2. So I'd be approaching a height of 1/2 from the bottom side. Anyway, we don't need that here, but you can verify that with a graphing calculator or application. Let's look at part B on this. Part B, so 23B is actually wrong in the back of the book based on how they wrote it. So they have the sequence n² -1/2 plus n. And once again, doing the same tactics, I'm going to divide everything by n². So I'm just going to try and do it in here. So I got, that's the biggest power of n, right? So if I do that, this ends up being equivalent to n² is 1 minus 1/n². And then on the bottom, I've got 2/n², and then plus n/n² is like 1/n. I can cancel out an n on top and bottom there. So anyway, if I take the limit here as n goes to infinity, then what happens here? This is going to go to 0. This is going to go to 0. This is going to go to 0. Okay. And so ultimately, it's going to end up being 1 over something approaching 0 in a positive way, and then that goes to positive infinity. So this is actually a divergent sequence that doesn't have the, the limit approaches positive infinity there. And that's what should be in the back of the book for this problem. But what they really meant to do is they meant to write this as 2 plus n². So let's redo this problem the way that the book apparently meant to have it. And so 23B alternate version, corrected version, I guess, would be, what if we had the sequence n² -1 over 2 plus n²? Well, the reality here, if I'd taken the limit as n goes to infinity of this thing, I can do a similar deal where I divide top and bottom by n², which means I can divide each term by n². And then, of course, doing that, what happens? This is gonna go to 0. This is gonna go to 0. But then this is gonna go to 1, and this is gonna go to 1. So basically, it ends up being 1 minus 0, or 1 on top, over 0 plus 1, or 1 on the bottom, which actually converges to 1. Okay, so it would be convergent if they would have had n² in the denominator of this sequence. So I just want to make sure you're aware of that. All right, let's keep plugging away. So you can see some of these are quick and easy hitters as long as we look at them correctly. Let's look in exercises 27 through 42. We've got a couple of them. Let's just look at, I'm going to do a couple odds here, but if I've got, I want to know on number, let's just look at 29. The question would be, is this increasing, decreasing, or which would mean it's monotonic, or is it not monotonic at all? In other words, is it neither increasing nor decreasing? So on number 29, they have the sequence 1 minus 2n² all over n². So basically what I want to do, let's go ahead and look at what this is if we let some specific values of n go here. So if n is 1, what's the first term? Well, it'd be 1 minus 2, which is minus 1 over 1, which is minus 1, right? If n is 2, then we've got 1 minus 2 times 4. So 1 minus 8 is minus 7 over 2² is 4. And then, which, that's minus 1.75. So definitely we know it's not increasing, right? It could be decreasing, or it could be neither increasing nor decreasing. Let's just do one more here, just kind of see what's happening. So the third term, n equals 3, so that's 9. So it's 1 minus 18 is minus 17 over 9² is 81 here. So minus 17 over 81 is, if I did that right, no, not 81, my goodness. 3, it's the third term, n equals 3, so that'd be 9. Minus 17 over 9 is minus 1 8/9, or minus 1.8 repeating. Anyway, so it looks like it could be getting, you know, smaller as we go. So it could be a decreasing one here. So let's just check that out a little bit and then say, okay, so now what do we do to verify that? So we're going to let a sub n, so a sub n, the value of the nth term, is going to be 1 minus 2n squared all over n squared. So I never, when I was talking today on geometric and arithmetic sequence, I could have just said a sub n is the value of the nth term. I was using words, but that is the value, you know. So basically we write this out as a sequence would be a sub 1, a sub 2, a sub 3, etc. So that's the value of the first term, second term, third term. I know I was calling the value of the first term a earlier, but we could have also called it a sub 1 to kind of match up with this book. But that was stuff you did in the past. But anyway, we've got this here, the value of the nth term, and then really what we can do is we can use some algebra and try and rewrite this. So if I rewrite this, I'm going to get 1 over n squared and then minus 2. And if I do that, just using rules of fractions there, basically the value of the nth term, I've got 1 over n squared, and then I'm going to subtract 2 the same, you know, from every single term. So this part here really doesn't matter. The minus 2 doesn't really matter because I'm doing it to every single term. But what do we know about 1 over n squared? Well, 1 over n squared, of course, we have y equals 1 over x squared. That was one of our base graphs from, you know, chapter 1 and calc 1. Anyway, what happens as x goes to infinity, or in this case n goes to infinity, so the reality is it would, you know, it would be dots out here for your n's, but out at infinity, the limit as n goes to infinity, what we have here is this is getting closer and closer to the x-axis, and is actually decreasing. So since 1 over n squared is decreasing, that means that 1 over n squared and then minus 2 as a sequence, as the value of the next term, is also decreasing. Therefore, this sequence overall right here is decreasing, and which also means that it is monotonic. Okay, so hopefully that makes sense for you. But doing a little rewrite there is a nice little algebra trick. Let's look at one with trig. I know we tried to avoid trig, but it seems like Coach Ryle always likes to put in trig in the homework. So we say we're getting away from trig, and then there's a trig one in the homework on number 30. So let's just do 31, see if we can figure that one out together. So we got the integral of cosine of 1/3 n pi, which I'm going to write that as n times pi over 3, and think of it that way. And then let's just write this out a little bit. So really what I have, and I'm going to write it out, when n is 1, it's cosine of pi over 3. When n is 2, it's cosine of 2 pi over 3. When n is 3, it's cosine of 3 pi over 3, which is cosine of pi, etc. So we're going to keep going here. Once again, the goal of this is to find out, is this increasing, decreasing, or monotonic? Okay, well, if I come up with what those are, remember the sine of pi over 6 is a half, so that means the cosine of pi over 3 is a half. And then the cosine of 2 pi over 3, we just got to figure out what quadrant we're in. That's also going to be a half, but we're in quadrant 2 there. So in the quadrants, you know, the unit circle, pi over 3 is here, 2 pi over 3 is here, and cosine is your x value. So now it's going to be negative a half. So the reality is it could be decreasing, but we're not an increasing sequence because the value of the first term compared to the second term We have A1 is greater than A2. So let's find out on the next one. Cosine of pi, the x value is -1. Okay, so we're good there. Let's go a little bit farther though. Let's do another one. So if I've got cosine, because what happens here is cosine can never be less than -1. So for this to be, we do have that A2 is also greater than A3, but can that keep happening here? I don't think so, because cosine can't be less than -1. So if we have cosine of 4 pi over 3, now I'm over here, once again, quadrant 3, and the base is 1/2, so this is going to end up being -1/2 again. And so what we notice is that from, this is A3, this is A4, we notice that A3 is actually less than A4, which, you know, that would not be decreasing, it's not going downhill. So we have this term is less than or greater than the next term, but then in a different spot we have this term is less than that term. So anyway, this is contradictory here. So basically this is neither increasing nor decreasing, or in other words, this is not monotonic. And we can just give that by counter examples here. Might be a convenient way to do that. Long story short, for some values of n, a sub n is greater than a sub n plus 1 for some values of n. For other values of n, we have a sub n is less than a sub n plus 1. And because of that, since we have contradictory things going on here, it's not monotonic. It's not going to be increasing or decreasing. Okay? Let me look at one more, just not an example, but let's just look at a sequence, you know, a constant sequence like 2. Well, if I have 2, then that's going to be, if I list out the elements, it's 2, 2, 2, etc., right? So the question is this monotonic? The reality is it is monotonic, and if you say, is it increasing? You could say, yeah, it's increasing, because if I take the value of the nth term, let's just do that somewhere. What is the value of the nth term? We'll call it a sub n. The value of the nth term is 2, right? And the value of the n plus first term is also 2. So what we have is that a sub n is less than or equal to a sub n plus 1 for all n, elements of the natural numbers, of course. So since this is true, then this is going to be considered, we could say this is an increasing sequence. But we could also say that a sub n is greater than or equal to a sub n plus 1, since it's equal, which would mean that this is a decreasing sequence. So this sequence in particular is not only an increasing sequence, considered increasing sequence, it's also considered a decreasing sequence. And that makes it very important to note that Professor Ryle says, I really like it when we talk about increasing to mean strictly increasing, which means it only goes uphill left to right. So a strictly increasing would not allow that equal sign, or strictly decreasing would not allow that equal sign. But that's not the definition here for an increasing or decreasing sequence. So it's okay to stay the same as you go to the right. And so ultimately what we can say is this sequence is what? It is monotonic. So it is monotonic. All right, so just a simple example, but just wanted to clarify the definition for you. So good thing that I don't teach anything but Calc 2, because otherwise I'd be out of time and have to go to my next class. So anyway, we'll just keep rolling here. I wanted to do a couple more for you. Let's look at number 43. So if I look at number 43, and of course you can feel free to try these hopefully on your own and make sure that you can get them, not just follow along of me getting it. We're just trying to see if this is bounded. All right, so we've got n squared plus 3 over n plus 1. And the question is that a bounded sequence? Does it have an upper bound and a lower bound? So it may be worth looking at what these values are and how they're acting. So if n is 1, we would get 1 plus 3 is 4 over 2. So we're going to get 2 for the first term. If n is 2, we get 4 plus 3 is 7 over 3, so 7/3. If n is 3, what do we get? We get 9 plus 3 is 12 over 4, which we get there. I'm going to do one more here. If n is 4, we get 9 plus 3 is 19, and 19 over 5, so 19/5, which is a little bit less than 4. But anyway, it's going to keep going. So the question might be, how do we determine if that's bounded? Well, if you notice here, couple of things. First of all, the smallest it's going to be is 2, because what happens? This thing, n squared plus 3, grows at a much faster pace than the denominator function of n plus 1. So since n is going toward positive infinity, then the farther out we get to the right, the more the numerator is going to dominate. It's going to get bigger and bigger compared to the denominator. So the smallest this is going to be is when n equals. This is actually the lower bound. This is a lower bound. Now 0 is also a lower bound because this would never be less than 0, right? So 0 is a lower bound, but 2 is actually what we call the greatest lower bound. Okay, so it is bounded on the bottom by 2. So then the question would be, well, what happens as we keep going? Do we hit an upper bound as we keep going out here? The easiest way in this case to do that is say, hey, what limit do we approach? What does this approach as n goes to infinity? Well, to figure that out, what we can do is divide by the biggest power of n everywhere. And if I do that, we know that this goes to 1, this goes to 0. 1 over n is what this is equivalent. That goes to 0. And this, of course, as n goes to infinity, goes to 0. So this would, as n goes to infinity, our sequence would actually approach 1 over 0. And, of course, we're going to 0 in a positive way because we're adding here. And n is a big positive number. So that's a positive 0. So this actually explodes to positive infinity. So because the numerator continues to grow at a much faster pace than the denominator, these outputs as n goes to infinity get bigger and bigger and bigger. And so this sequence, as you keep going, gets bigger and bigger or approaches positive infinity, which is actually means it's a divergent sequence, which also means that it has no upper bound. And since it has no upper bound, that also means that it's not bounded. So we had, and this is a case where we have a greatest lower bound, or it is bounded on the bottom side, but it's not bounded on the top side. So in general, what can we say overall about this sequence? Whether or not it's bounded, this sequence is not bounded. So we went out of bounds on the top side. If you go out of bounds on at least one side, then it's not going to be bounded. Okay, so we got one more here before I run out of time and energy. Anyway, so 49. Let's look at 49. 49 is a couple things. It says use the theorem to prove that the sequence is convergent. So basically, we have a sequence that we think is convergent because it says to use the theorem to prove that it is. So for number 49, it says go back to number 35. Well, let's go back to number 35 and just see what that is. What we have, this is kind of a unique one. We haven't really looked at one like this, so I wanted to look at this too. So 5 to the nth power over 1 plus 5 to the nth power, and we got that sequence. Okay, well, we need to remember what that theorem says, and what the theorem says, 8.2.10 on page 690, it says for a theorem, if we have a bounded monotonic sequence, monotonic sequence is what? It's convergent. All right, so all we got to do is show two things. If this sequence is bounded and it's monotonic, which means it's either increasing or decreasing, then if we can verify those two things, then we can say that it is convergent. All right, well, so how do we do that? We get to pick one to start with. So let's just show what happens as we go. So if we can look at a sub n here. So a sub n is going to equal the value of the nth term, 5 to the nth power over 1 plus 5 to the nth power. What we could possibly do is rewrite this. Might be an idea. We could drop that 5 to the nth power down to the bottom. And if I do that, write it as 5 to the minus nth power, what we have on the bottom is 5 to the minus n power plus 5 to the nth power. Okay. Anyway, so we could have something like that. Now, if this is, first of all, if this is a function, is this defined for all n's? I mean, this is really, if we look at it, it's 1 over 5 to the nth power, and then plus 5 to the nth power, but this is in the denominator. So we can say, hey, do we have a problem if we were graphing this, or is this a continuous function? If this was in terms of x, are we okay? Well, you know, remember, we're taking n is getting big here, so n is greater than or equal to 1, right? N is a natural number and it's getting big. So this is not a problem at all. We're never dividing by 0 here because 5 to the nth power gets huge, right? So, and then 1 over 5 to the nth power is 1 over something that gets huge, which goes to 0. So anyway, and then, so 0 plus infinity would be 0. If we add, not 0, but infinity, 0 plus infinity. So if we look at the limit as n goes to infinity of a sub n, it's going to equal 1 over something that's going to 0 in a positive way, plus something that's going to infinity. Well, I don't care what you add to infinity. If it's positive, it's going to be infinity. So this is like 1 over infinity, which goes to 0 in a positive way. So this is approaching 0 in a positive way. And anyway, so that would be possible bounding of it. So now that would be, could I ever be negative? Could I ever get to a negative number? Well, no, because when n is 1 or bigger, this is a positive number and this is a positive number, and 1 divided by a positive number is positive. So I could never get a negative number. So I'm bounded on the low end, okay? Bounded on the low end. So let me erase this and start over. Okay, so let's just rewrite my sequence here. So we had 5 to the n over 1 plus 5 to the n. So it has a, it does have a lower bound of 0. Okay, because this is always going to be, this value right here is always going to be greater than 0, right? So this is always greater than 0. So I do have a lower bound of 0. The question, do I have an upper bound? And so if I take, what's the biggest it would be? Well, let's list out some terms here. And so I'm just gonna write n equals 1, n equals 2, n equals 3, n equals 4, kind of see what's going on here. So doing that, if I plug in 1, I get 5 over 1 plus 5 to the first is 5/6, right? If I plug in 2, I get 25 over 26, right? If I plug in 3, 5 cubed is 125, and then over 5 cubed plus 1, which is 126. And of course, if I plug in 4, I've got, well, 5 to the 4th power. I don't know what that is, but I know what 5 squared times 5 squared is. 25 squared is 625. So 5 squared, quantity squared is 5 to the 4th. Anyway, over 1 plus 5 to the 4th would be 626. So we're seeing a pattern here. So this is kind of nice writing these out. What we get is a numerator and a denominator where the denominator is always one bigger. It's just one bigger than the numerator, right? And so ultimately this approaches and what dominates as n gets big? It's the 5 to the n power dominates, right? But anyway, so what happens here is this would approach 1 from the bottom side, right? So there is an upper bound of 5. Upper bound, not of 5, sorry, of 1. I was thinking ahead here. The other thing, could we possibly do something similar and divide top and bottom by 5 to the nth power? Well, I could, and then use law of fractions there, right? So dividing top and bottom by 5 to the nth power is kind of similar to what we did. And then what happens? Well, 1 over 5 to the nth would go to 0, and then this would equal 1, and this would equal 1. So the limit as n goes to infinity does exist and equal 1. So we could do that as well. So we do, but then I guess listing it out shows us that we can never get a number that's bigger than 1. So that is an upper bound. In fact, this is the greatest upper bound there. Now the least upper bound, you know, we have a lower bound of 0, but if you say, hey, what's the least lower bound, it might actually, I believe it would actually, excuse me, this is not the greatest upper bound, this is the least upper bound. Starting to wear down. That's the smallest upper bound we could have is 1. A 10 is an upper bound also, because we'll never hit above 10. But anyway, the least upper bound is 1. But if I said, hey, what's the greatest lower bound? It would be bigger than 0, right? It would probably be that 5, 6. So I'll let you confirm that. So anyway, we've satisfied half of the theorem here by showing that it's bounded. So this sequence is bounded. Now all I got to do is show that 5 to the nth power over 1 plus 5 to the nth. So we just showed that it's bounded. Now I've got to verify that according to the theorem that it is, to make it convergent, it has to be monotonic, which means increasing or decreasing. So the question is this increasing or decreasing? Well, as I was looking at that, we're approaching 1. So if I was thinking of this as a function, it looked like we started at 5, 6, but then we kept getting closer and closer to 1 from the bottom side. So it looks like it could be an increasing function. And in fact, it is I believe it is an increasing function here. So the question is, wait a minute, decreasing or increasing? Well, let's find out. How could we do that? Let's go back to what we did. If I called this f of x equals 5 to the x power over 1 plus 5 to the x power, I could look at that and say, what type of function is this when x is greater than 0? So if x is greater than 0, what type of function is this? Increasing or decreasing? Well, how did we evaluate increasing or decreasing functions in Calc 1? We use critical numbers. We split up with critical numbers, right? And then we took the derivative. We did a first derivative test. If the first derivative is positive on an interval, then it would be an increasing function. If it's negative, it would be a decreasing function. So let's kind of memorize how we did that back in Calc 1. And so once again, let me rewrite this the way we did early, 5 to the minus x plus 5 to the x, and let's take f prime at x. See if we want to do this. So f prime at x. So first of all, critical numbers is where the derivative is 0 or undefined. For any positive x's, well, let's figure out the derivative first. So this would be 5 to the minus x plus 5 to the x quantity to the minus 1 power, if I do it that way. So I'm going to use a power rule, not the quotient rule. So I'm going to take that minus 1, drop it in front. I'm going to take it times that to the minus 2 power, but then times the derivative of what's inside by the chain rule. So now the chain rule, the derivative of what's inside. So if I got the derivative of a to the x, it's a to the x natural log of a. So the first one is a to the x, so it'd be 5 to the minus x times the natural log of 5. But once again, using the chain rule again, that wasn't just to the x powers to the minus x, so I got to take it times -1 by the chain rule. Okay, and then plus the derivative of 5 to the x is 5 to the x times natural log of 5. And that's just an x there, so we're fine. So anyway, now let me try and rewrite this on what f prime is then. So f prime is going to equal, so I've got a -1 on top. I'm going to take the next part to the denominator, and it's going to be 5 to the minus x plus 5 to the x quantity squared. Okay, so these are, whether they're, by the way, these are all positive numbers, but then we're quantity squaring it, right? So that's going to be positive, so that doesn't really impact the sign. What do I got left there from kind of the red and blue stuff? Well, I've got -1. I can pull out a natural log of 5. And then I've got -1, 5 to the minus x, and then plus 5 to the x. Okay, well, what do we know here? We're trying to find out the sign of f prime when x is greater than 0. Okay, by the way, critical numbers is where the derivative is 0 or undefined. So I can try and figure out where the numerator is 0 and stuff like that, but that might be when x equals 0. So I'll let you verify that. But anyway, so what happens here, what's the sign of f prime? Natural log of 5, this is positive. This is negative, so we have negative so far. This is positive, so we've got a negative value. And the question is, what is this then? So that's on top. So this is 5 to the x plus, I'm writing this one first, plus a negative or minus. So now it's minus 5 to the minus x. So 1 over 5 to the x power. So what is this? This ends up being positive, right? Because this is a tiny number when x gets huge. This is a big number. So anyway, big positive number. So this ends up being a positive number. So we have negative times positive divided by positive ends up that f prime is less than 0 when x is huge, which says what about f? Therefore, f, my function, is decreasing. So something doesn't jive on that. That's why I kind of hesitated. But because I think when I drew my graph, I was approaching it from the bottom side, but maybe, you know, I'm not sure what's going on there. So I messed something up there. But anyway, it looks like f is decreasing if I did my derivative right, which means that it's monotonic. So I could use Calc 1 methods to show that f, my function, is decreasing by taking the derivative and looking at the sign of it on that interval out wide. And so it's monotone, and I already showed that it's bounded, therefore by the theorem, the sequence is the sequence a sub n 5 to the nth power over 1 plus 5 to the nth power converges by the theorem. All right, so I'll let you double check all that.